Okay, next talk is from Choudhury, and he will talk about cosmology and high-redshift universe with SKA.
Okay, sorry about this. So taking cue from the previous talk, I wanted to discuss about another so-called classical astronomical observatory, which works in a different band in radio. That is the Square Kilometre Array. The Square Kilometre Array is interesting for India as well because it's a significant partner in this multinational project. So the Square Kilometre Array, the so-called phase 1, and that's what we will concentrate in this talk. So the SK1 is expected to be kind of completed somewhere around 2025. Again, a similar timeline as TMT. There will be another phase which will be the full SK, but that is still not really planned as yet. There will be dishes in South Africa, and that aspect of the SK will be called SK mid. And then there will be low frequency dipoles in Australia, and that will be called SK low. So mid means mid frequencies, low is low frequencies. So that's how this thing is divided roughly. The largest baseline you have is somewhere of the order of 100 kilometers, depending on whether you are looking at the Australian site or the South African site. And the name comes from the fact that the effective collecting area is of the order of kilometers square. And that's 5 to 10 times more than any existing telescope at the moment. I already talked to you about the sites. So the Australian part will be set up in Western Australia, whereas the South African component will be in the Karoo Desert. These places were chosen based on the fact that they have very low population density, empty space, less RFI, and so on. This gives the idea about what timeline are we talking about. So this is quite a busy plot, but I wanted to just highlight a few things here. So currently we are somewhere here. So essentially what has happened is the design phase of the instrument is over. Various components, the design of the various components are being reviewed and being accepted and so on. This C0 is when one expects the first construction contract to be awarded. So everything will slip if this C0 slips this way. Then we have time for, there are timelines for science commissioning, verification, shared risk proposals. One thing which is interesting is the KSP proposals. KSP stands for Key Science Projects. These Key Science Projects, as defined by the SK office, are those projects which are extremely resource intensive and probably consists of large group of people worldwide. And these will take a significant amount of time of the telescope to run, maybe surveys, big surveys, thousands, 2000s of hours. And expects these KSP proposals to start somewhere around 2025 or so. So that's the timeline I mentioned. And that's when we will start getting the initial science results. Of course, by definition, these KSP proposals will take few years to get complete. So the headline grabbing science will probably take some time to come. Of course, the PI proposal starts somewhat later, somewhere around 26, 27. So this is the broad timeline with which the project is working at the moment. The countries participating in the SK, so this is the color which you should look for the countries which are participating. So currently there are 12 countries. The host countries are, of course, Australia and South Africa and UK, where the headquarters are located. And of course, you have India on the map. Now, how does SK1 is expected to perform compared to existing telescopes? So what has been plotted here is the sensitivity versus the frequency. And this is the first phase of the SK mid part, which goes to relatively high frequencies, and this is the SK low component, which goes to lower frequencies. And you can see, I mean, it's like 5 to 10 times more sensitive than any existing telescope at the moment, like JVLA, the upgraded GMRT, LOFAR, and so on. You can plot various other things. For example, another thing which is interesting for cosmology is the survey speed. How quickly can you cover the sky with a given sensitivity? Here also, SK, once it comes up, will be much better than the existing telescopes, 10 to like almost 100 times better depending on which frequency band you are looking at. So again, this is something to look forward to. I also wanted to highlight one fact, because this talk is in India, is if you concentrate on what we call this meter frequencies, that's something like 300 megahertz to 1 gigahertz. Till SK comes up, the most sensitive, most efficient and sensitive telescope you have is what we call the UGMRT. That's a telescope in India. So let me just take this opportunity and spend a few slides on the GMRT. So that's the Giant Meter Wave Radio Telescope. You can see the antenna, and this is how they are distributed in a Y-shaped array. It works in a wide range of frequencies, situated at a place 80 kilometers from Pune. And the upgrade is almost complete, so it's being upgraded to what we call the upgraded GMRT, so UGMRT, and that is designated as one of the so-called SK path finders. Because of the upgrade, what has happened is the frequency coverage has increased. Earlier, you could only look at specific frequency ranges, what is being shown by these whitish bars. But now you can see, you can go from almost 120 or so to 1450 megahertz almost seamlessly. So that's the best part of the UGMRT. And because of that, there are various advantages now. For example, people who are doing spectral lines, because of this broad coverage, it gives significant increase in the redshift space if you are, for example, doing H1, but it also gives access to other kind of lines, maybe molecular, other complex lines, and so on. If you are interested in continuum imaging or pulsar observations, the sensitivity simply has improved by a factor of 3, and that's something which was shown in the earlier plots. And this is, again, let me repeat the statement that only SK phase 1 will do better than the UGMRT at meter wavelength. So till then, UGMRT is the best you have. So let me now talk about the Indian involvement in the Square Kilometre Array. India, has been associated with the SK from the beginning, in various formal and informal manner. It formally joined the SK project in 2015. So over the years, we have actually coordinated the activities within India, the SK-related activities within India, to quite a bit. So basically, the activities are coordinated by what we call the SK India Consortium. These consortium, the members of this consortium are various organizations. They can be research institutes, universities, colleges, or there can even be individual members. So as of now, about 20 organizations are member of the consortium, and then this consortium has various kind of subcommittees, some looking after science, some looking after the technical aspects, and so on. So the science activities currently are coordinated by what we call the SK India Science Working Groups. They are very similar to the international science working groups that exist in SK, but these are more India specific. And Indian astronomers are kind of interested and somewhat involved in almost all the key science areas in the SK. If you are interested, for example, in the science cases which are relevant for India, you can take a look at the special issue of this Journal of Astrophysics and Astronomy, where various articles have been published highlighting the Indian science case, and many of the authors are probably sitting in this room. Now, if I go to what kind of science you are going to do with the SK, given its wide coverage in frequency in wavelength, again, the science case goes all over. There are all sorts of science cases, and this is a table which is taken from the science book published by the SK office, maybe a couple of years, 2015, so 3 years back, roughly. So it starts from the cradle of life and astrobiology and goes up to very high epochs like the cosmic dawn and the epoch of reionization. So of course we won't have time to go through all of them, but here what I will do is I will concentrate on things which have to do with cosmology and high-redshift universe. Even within that I will choose things which I like and probably is quite relevant in India because the Indian scientists are working there. So for example, there is a science case which has to do with galaxy evolution probed by neutral hydrogen, because the number of galaxies observed will just increase massively with the Square Kilometre Array. There will be galaxy evolution probed by the radio continuum because of the correlation between the continuum flux and the star formation rate. So one expects to probe star formation rate independently till up to redshifts of 4 or so. Cosmology and dark energy and epoch of reionization. So let me spend some time on few of these things. One thing which is very relevant for cosmology is the neutral hydrogen intensity mapping. So the basic idea is you will probe something like the correlation function on the power spectrum of large scale structures. So typically you would have just gone detected galaxies and then calculated the power spectrum. The H1 intensity mapping allows you to do in a more efficient way, in the sense you don't try to resolve individual galaxies. You just go and look at a low resolution map of neutral hydrogen. And assuming these galaxies contain neutral hydrogen, you will see this neutral hydrogen signal. Whatever neutral hydrogen there is there in the galaxies will kind of show up here. If you are just interested in large-scale properties, large-scale power spectrum, this is good enough. So interestingly, some of these ideas was first presented by Somnath Bharadwaj and Shiv sitting here in 2001. Somnath was there during the school, and this has really picked up. They were doing the calculation again, keeping GMRT in mind. So if you want to do cosmology with H1 intensity mapping, the advantage with the SK is because of its large field of view, you will cover a huge volume compared to other similar, other surveys in other wavebands. So that essentially helps you to get the power spectrum. So this is the error on the power spectrum at very large scales, K of this range. And you can see, so this has been plotted for various SK surveys. So you can see that SK is going to be the kind of, is going to provide you the most accurate measurements of the power spectrum at large scales. And then this has implications for whether you want to probe non-Gaussianities, relativistic effects, and so on. So this is a wide field out there. Then you can also probe H1 absorbers and galaxy evolution. So basically, this is a plot of omega H1 versus redshift, and this is the part which is like poorly constrained observationally. Again, one is hoping that SK will actually plug this hole. I believe that SK kind of precursors and pathfinders are already doing nice surveys where Indians are involved in, and again, SK will probably change the game altogether here. The last part of my talk is what I'm interested in, that has to do with the 21 centimeter signal from the EOR. So as the universe gets reionized, you can probe how the 21 centimeter signal, the so-called brightness temperature, changes across redshift. So this, for example, are predictions for some simulations which were led by Girish sitting here for different type of reionization histories. So with the current Planck data, probably this is the one which is relevant. The numbers quoted in the brackets are the values of the optical depth. Of course, at least with the first generation of radio telescopes, one doesn't hope to make these maps because they will be too noisy. The hope is to go for some statistical measures as usually done. So the standard thing would be to calculate the power spectrum. So again, if you look at this model, so the typical theoretical predictions lie somewhere here. So we expect the signal to be of the order of kind of few millikelvin. The current observations, the data are where, I mean, of course, GMRT was the first one to get an upper limit, which was way up here, but this was the first point. But then other experiments have done much better. Paper, in fact, did very well, except that recently they have retracted their points, so these points are expected to go up. So currently, the best constraints we have are from an experiment called LOFAT. Yeah, I'm almost done. The other thing which interests me is, again, 21 centimeter signal, not from the epoch of reionization, but slightly early, before the reionization starts. That's called the cosmic dawn, when the first stars were being formed. So the signal will look somewhat different. So these were done using some simple radiative transfer calculations during the cosmic dawn, taking into account heating and Lyman alpha coupling and so on. When we were doing the simulations, again, we were calculating power spectrum and so on, but when we looked into the map, we realized that if one can detect the signatures of these individual sources, this is like one galaxy which has formed, which has given its signature. So we got interested whether we can just detect this one, and that will be, then you're not doing statistically, you're just going and detecting a 21 centimeter signature of one galaxy. So it's like detecting a galaxy at high redshift when the first stars were being formed. So these things have very, very rich structures. So I'm not going into the details, but we went ahead and studied the viability. The thing is, these objects are very rare. So if you just, but the signal is also very weak. So if you just stare at a sky for a long time, you will integrate it. It will be, the map will be very, very high, will have very little noise. But it may happen that there's no source in that field. So one has to come up with very smart survey plannings with a combination of shallow surveys and deep surveys, and that's something which we are looking into. Of course, I didn't at all talk about systematics, the foregrounds and so on. So some of those things are also being we are trying to study while doing these things. So I think I've come to the end of my talk. So let me leave this slide, which gives you some idea about some of the interesting science areas and the kind of questions SK is going to ask. So thank you very much.